So hello everyone. Welcome to the first talk of the Stefanich-Tannaka Duality seminar. So we're basically going to talk about Stefanich's version of the Tanaka duality for geometric stacks. So something that Lurie proved. So this is like a like a version without the tameness hypothesis. We'll kind of see what I mean by that later on. So initially, I'll try to come clean. So initially, the plan of the talk was supposed to be me just going through the kind of stuff that people have done to get rid of the tameness hypothesis and everything, and what Stefanich does. But that would be boring. That would be like 30 minutes or something. So I was like, yeah. So I just decided that okay, I'll just talk about I'll just talk some stuff from SAG and DAG 8, I believe. So basically, just to give you all just a recap of of Lurie's stuff. So this is fairly expository. Like to be honest, you kind of assume that you know this stuff. So I mean, so there's not much here, but we'll just see a recap, right? So we'll just see a bunch of theorems and stuff, and there's going to be some motivation and why do we care about what we are going to do for the seminar and blah blah blah. So we'll see. Let's go. Okay, so here's the outline. So first I'll just say a few words, like just some motivation, not math. But since I'm using slides, so the words are also going to be in the slides. So and then I'll basically define these the objects, like starting with quasi-geometric stacks and morphisms. Then we'll see the Tannaka duality statement for quasi-geometric stacks. And then we'll see geometric stacks and then the Tannaka statement for geometric stacks. Okay, there's a typo I can see. Never mind. And then we'll see what Stefanich does and just give a rough proof sketch so that everyone has an idea of what's to come for the seminar. Right, so we start off with some motivation. So we start off with an affine algebraic group G over some field K, and so here's some typical notation like these. So this is my R valued points, and this is like representation, finite representation category. And so for the classic Tannaka duality statement, the slogan is, so we have this action of GR, that is R valued points, on the forgetful function that you have from finite representations to so this is like the category of projective R modules with finite rank. So you have an action that is given by tensoring R with phi. So you have these R tensor V. The Tannaka duality basically is about recovering like this G of R from this action. So that is the basic premises of the classic Tannaka duality. And now, so here's a reinterpretation that Lurie does. So basically, Lurie does it in a general setting, but we'll only see it for geometric stacks. So we want to interpret Tannaka duality as a statement about the classifying stack of an algebraic, right? So the classical Tannaka duality statement can be interpreted as a special case of the following statement. So the construction, so here's a construction which has you have map from spec of R to B of G that goes to E upper star from rep of G to mod R. So this determines a fully faithful embedding from the category of R value points of PG to the category of symmetric monodal functions from rep G to mod R. So this hard is basically subcategory that is spanned by discrete objects. So the question that we care about is the following. So for what kind of object X can we expect an analog of the previous theorem? That is a map like spec R to F, so that can be recovered from its pullback. Like Q, so this is like quasi-coherent sheaves on its R mod. By the way, feel free to interrupt me if I'm too fast, because these are slides and there's always a possibility of that happening. Right. So here goes nothing. So we start off saying what a quasi-geometric stack is. So we started Lurie's definition. So a quasi-geometric stack is a function from Cn to S. So this is basically spaces, the category of spaces, and we'll see why we have like this. Why it doesn't matter if we just have like S or I guess ball hat, whatever you want to call it. So that satisfies the following. So X satisfies descent with respect to the FPQC topology. So if you don't remember, it is like the Fidel. So it is like a short form for like Fidel-Montclair a quasi-compact. So that means like basically it is a kind of open-dict topology where like so this map. So if you have these, if you have an open cover UI to X, and then you take the map like the induced morphism, that is the disjoint union of UI to X, it is faithfully flat and quasi-compact. So that is like FP, that is faithfully flat, Fidel-Montclair, and QC is quasi-compact. And then the diagonal is quasi-affine, and then there exists a connected infinity ring A and a faithfully flat morphism from spec A to X. So an example is basically like the moduli stack of formal groups, like one-dimensional formal groups, and then you can it's not hard to see that if you take a quasi-compact, quasi-separated spectral algebraic space, it is also an example. So we'll see more examples as we move on. Right, so here's a proposition. So you start with a functor, like from the C out C into S hat. Then the following are equivalent. So the diagonal map is quasi-affine, and for every pair of connective infinity rings R and R dash equipped with these maps from spec. So you have these maps from spec R to X and spec R dash to X. Then the fiber product is quasi-affine. So this is like, just gives you a like equivalent statement for what it means for the diagonal to be quasi-affine. It's pretty classical stuff. For every connective infinity ring R and every morphism from spec R to X, the morphism F is quasi-affine. So far, so good. So here's a consequence. So if you have a functor from C out Cn to S hat with a quasi-affine diagonal, then any morphisms from spec R to X is quasi-affine. So R is a commutative. And so here's a converse statement. So again, you start off with a functor from C out Cn to S hat. Which is a sheaf for the FPQC topology, and suppose there exists a morphisms from spec R to X, which is representable and faithfully flat. If F is quasi-affine, then the diagonal is quasi-affine. So basically, the converse. Now, using last proposition, we have the following characterization. So suppose you start off with a functor again from C out Cn to S hat. Satisfies descent for the FPQC topology, and you have a morphism from X dash to X such that this X dash is like, so it is also a quasi-geometric stack, and F is quasi-affine, representable, and faithfully flat. Then this X that you have, that is also a quasi-geometric stack. So right. So I'm not going to talk about the proof, but okay. So yeah, I'm not going to talk about proof for most things, but for this one, let's see. So it's like a proof sketch. So since like X dash is a quasi-geometric stack, so you can by definition you can choose a connective infinity ring, say R, a faithfully flat morphism from spec R to X dash. Then you just replace F by F compose F tilde. Then so you can assume that this X tilde, which spec R is a co-representable functor, and then like this diagonal map for X is quasi-affine. So it's just using the last proposition that we have, which implies that it is a quasi-geometric stack. So it is like pretty straightforward application of the converse statement that we saw. That is the last statement. Right. So we have the following probability. So you start as a simplicial object in this category of functors from C hat to S hat. I satisfy the following. So this X0 is a quasi-geometric stack, and so this is like a groupoid object in this functor category. And then the face map x1 to x0 is representable quasi-affine and faithfully flat. And the geometric realization is basically a quasi-geometric stack. So you can use the previous theorem to prove this. Okay. Right. So I believe. Okay. So now we'll see what a quasi-geometric morphism is. Okay. So suppose you start off with a natural transformation. Suppose you have a natural transformation between these two functions from C hat to C hat Cn to S hat, then it is said to be quasi-geometric if for every connective infinity ring R and every morphism from spec R to Y, this fiber product that you have of the spec R X it's a quasi-geometric stack. Right, so we'll see some properties. Again, proofs are pretty straightforward. I mean, I think this is mostly from SHG and DG, so you can just find it there. So you start off with a pullback square that looks like the following. Right? So you have f dash from x dash to y dash, and f from x to y, and morphism from y dash to y is g. So an FPQC sheaves. If f is quasi-geometric, then so is f. Moreover, the converse holds if G is an effective epimorphism. Right, yeah, to make sure I'm not going too fast. Okay, right, so another proposition. So suppose you have a natural transformation again between these two functors. And so here, okay, this is a typo. So if x dash is a quasi-geometric stack and f is quasi-geometric, if it's a quasi-geometric morphism, then x is also a quasi-geometric stack. All right. Now we want to see how this quasi-coherent sheaves on X. It's well behaved for a quasi-geometric stack X. Right. So here's the proposition. So you start off with a quasi-geometric stack. Then this Q X Cn is a complete Grothendieck stable infinity category. So we'll see what. So we'll basically see what Grothendieck stable infinity categories are later, but still, I'd like to do a bit of a recap, quote unquote. So moreover, this is like a stabilization of this quasi-coherent sheaves on X. Oh, right. So just recap. What is a complete Grothendieck pre-stable infinity category? So pre-stable infinity category is said to be Grothendieck pre-stable if it's presentable and okay, by the way, this is something that I've not mentioned. This is something I should have mentioned before, but this is more important if we move to Stefanich setting. But there's a certain reason why for this, for quasi-geometric stacks, so it doesn't matter if you use like this S or S hat, that is the spaces which are essentially small. So I mean, I'll not get into that, but right. So this is something that I should have mentioned. Okay. So right. So okay. So now you're seeing what pre-stable, Grothendieck pre-stable is. So pre-stable infinity category. So maybe a word or two about what I mean by pre-stable. I mean, we'll definitely see a pre-stable infinity, like all these things. But I don't know. So you start with an infinity category C. And then it is like it admits finite colimits, and it's pointed and all that. And then you have a suspension. You have the suspension. The suspension is fully faithful, and then there's like some other conditions that if you have. It's pretty standard, so maybe I'll sweep it under the rug for a moment, but. If I could write, I could write it down. But right, so you start off with a pre-stable infinity category. It is said to be Grothendieck pre-stable if it's presentable, and there exists a presentable stable infinity category C dash, and you have a T structure such that it's compatible with filtered colimits, and you have an equivalence of this form, right? So here's the thing. I mean, there's like, so as you'll also see here. There are like different ways of defining what Grothendieck pre-stable is, and But I've chosen this one because this makes sense to me. I mean, just there's nothing specific, like special about this, but there are like other equivalent definitions that we'll see. Right, so these are like analogous characterization of codely presentable infinity categories. So you start off with a presentable infinity category, then the following are equivalent. So one is this thing right here, like the thing that we have in the definition, that you have a presentable stable infinity category C dash, and this T structure such that it's compatible with filtered co-limits and C dash greater than equal to 0, that is the same as C. And and another one is C is pre-stable, and this functor loop C to C commutes with filtered co-limits. And the third condition, third definition is like its equivalent definition that C is pre-stable and the functor omega infinity from C to C commutes with filtered co-limits. And the fourth equivalent statement is that it is pre-stable and filtered co-limits are left exact. Right, so using this, we'll have the following reformulation for second last result of how it looks like. So basically how quasi-covariant sheaves look like for a quasi-geometric stack X. So again, you start off with a quasi-geometric stack, then this quasi-covariant sheaves on X is presentable, this category, and you have a T structure such that this Q car X, Cn, that is basically Q car X less than equal to 0. And this T structure is compatible with filtered co-limits, and it is right and left contained. Right. So now for our setting, we'll move to the Lean-Mumford stacks. That is TM. So I'll just call them DM stacks for simplicity. So you start off with a morphism of spectral GM stacks, and you say that the morphism is quasi-geometric if it's quasi-compact, and the diagonal map is quasi-affine. Right. So that is the definition of a morphism being quasi-geometric. So what is so a spectral Lean-Mumford stack is said to be quasi-geometric if the map X to spec XS is quasi-geometric S is distribution. If the functor represented by a spectral Lean-Mumford stack is quasi-geometric, then the spectral Lean-Mumford stack is quasi-geometric too. Like, you know, so interestingly, it's not obvious why the converse should also hold. Like more like why the spectral Lean-Mumford stack should be a sheaf in the first place with respect to the FPQC topology. So
sorry, can you, like, what was the last statement to the previous slide? Do you mean if your previous definition is quasi-geometric, then it works in this definition, and the opposite doesn't work?
Opposite, I mean, it's not obvious why the converse should, like, yeah, it does not always work. It only
Okay.
works if it is also seriously. So this is resolved when the spectral Lean-Mumford stack is also quasi-geometric. So here's a proposition. So you start off with a quasi-geometric spectral Lean-Mumford stack X, and this is like the function it represents. Then it is a hypercomplete sheaf with respect to that PQC topology and C outs. And so for this you have this corollary. So you start off with a functor that is represented by a functor from C out Cn to S that is represented by a quasi-compact, quasi-separated spectral algebraic space. Quite a lot of words, I know. The next is a quasi-geometric stack. So maybe I'll make a comment about this, like why the converse does not work, maybe later, or maybe we can discuss that in the over Discord. Right. Oopsie. Okay, there's something. I have to move this. Okay. All good. So now we are interested in understanding how finiteness conditions, including things like perfectness and compactness properties of quasi-coherent sheaves and quasi-geometric stack interact. Okay. So you start off with a quasi-geometric stack, and you take, so F is like a quasi-coherent sheaf on X, then the following are equivalent. It is almost perfect. So I mean, I can maybe recall what almost perfect. I mean, I think it's pretty standard. Okay, so let me just say it. So if you start off with the spectral Deligne-Mumford stack, so let's call it X, and you take a quasi-coherent sheaf F, and, then it is said to be almost perfect if for all affine objects, right? So say U, for all affine objects U in X, this F of U, it's almost perfect as a module over OX of U. Right, so as a module, so it's straightforward enough. And for all N in Z, the functor F dash to maps in these quasi-coherent sheaves F and F dash commutes with filtered colimits when restricted to Q co X less than equal to N. Okay, so for the case of perfect objects, you have the following proposition. So you have you start off with a quasi-geometric stack, and where F is like a compact object of Q co X, then it is perfect. So it's converse. Okay, there seems to be a problem. Okay. It's okay. The converse is not true in general. More about that later. So, right. So here's another proposition. So you start off with a quasi-geometric stack X, and the following are equivalent. So you have an integer n, decently created into like large enough, such that the global sections functor this F2. Right. So this carries this Q co X greater than equal to 0 to spectral greater than equal to minus n. And the other one is that this OX is compact. And third statement is that this functor, this global section's functor from Q co to SP, this commutes with small colimits. And fourth statement is that every compact object in F is compact, in Q co of X. And then it is a quasi-coherent sheaf is compact if and only if it's perfect. Right, so important corollary. So if you start off with a quasi-compact, quasi-separated spectral algebraic space, then an object F in Q co X is compact if and only if it's perfect. Okay. So far, so good. Okay, I think I'm doing good on time. So suppose, here's another proposition. So suppose you start off with a morphism X to X dash in the functor category functors from C out C into S, with X being a quasi-geometric stack and X dash being something affine, and suppose OX is a compact object of Q co X. Then the pullback that you have, this pullback of F upper star, this admits right adjoint F lower star. This F lower star, this commutes with small colimits, and then for every pair of sheaves like F and Q co X and F dash and Q co X dash, canonical map, this theta F dash that goes from F tensor. So, okay, so this is a typo. It's supposed to be mathcal F dash. Okay, so let me say it properly. So the map says theta mathcal F to mathcal F dash. So that goes from mathcal F tensor F lower star mathcal F dash to F lower star F. Yeah, F lower star applied to F upper star F tensor F dash. Okay, it's bad notation. So it is an equivalence in Q co X dash. So we'll see cases of the proof. So the first one I'm not going to do a thing because it's just falls from the adjoint functor theorem. For the second point, so let's see the second point again, so that this F lower star just commutes with small colimits. For the second point, so you note that if you take this composite, so after applying this F lower star, you take the global sections functor. So this can be identified with the closed section functions of X, and therefore it commutes with filtered colimits because we're starting with assuming that it is compact. Now, given that this X dash is affine, we have that this gamma X dash is conservative and preserves small colimits. Therefore, this F lower star should preserve small colimits as well. Okay, there are a few more like grammatical mistakes, but you know what I mean. So now for the third particle, let's see the third particle. It's this theta. So this is like an equivalence in Q bar X dash. So for the third part, oopsie. So yeah. So note that using the second part, the collection of objects is F Q bar X dash, for which this is an equivalence. It is a stable subcategory of Q bar X dash, which is closed under small colimits. Now, since this theta F dash is equivalent to the identity map from F upper star F dash, I mean, this is just something very good. That should make more sense if you just write it down to itself. It follows that the stable subcategory described above, it contains the structure sheaf OX dash. Okay, there's another typo. So that means that it coincides precisely with quasi-covariant sheaves of X dash. All right, so now we have like a weaker proposition where X dash is not assumed to be affine. It's just like, yeah, that should be called weaker. Yeah, I think so. That's right. So we start off with a morphism again, like from X to Y, in this category, functor category C out to S hat, such that every connective infinity ring A and every point mu in Y of A, the fiber product spec A X is a quasi-geometric stack with theta X mu, a compact object of with this Q bar X mu. Right, then the pullback from Q bar Y to Q X, this admits a right adjoint, that is F lower star, and this right adjoint commutes with small colimits. Right, so this continues. Now, so you start off with a pullback diagram like this. So you have a morphism. So this is like our original morphism X to Y. And then you have like a pullback diagram like this in the functor category from C out to S hat. Then the associated squares, you take quasi-covariant sheaves, so quasi-covariant sheaves of Y to quasi-covariant sheaves of X. So this is our F upper star, this is F dash upper star, and so on and so forth. And the Beck-Chevalier transformation G upper star, F lower star to F dash lower star, G dash upper star. It is an equivalence of functors from Q bar X to Q bar Y dash. And for every quasi-covariant sheaf F on X and J in Q quasi-covariant of spec of X, the canonical map from this F tensor F lower star J to F lower star applied to F upper star F tensor with J. So this is an equivalence in Q bar Y. So here's another proposition. So suppose you have a morphism of quasi-geometric stacks X to X dash, and okay, I don't know what this is. These things to talk about. Theta, so this OX is a compact object in Q bar X. Then for every connective infinity ring A and every point mu in X dash of A, the fiber product spec A times X, which is basically like X. So sub mu is a quasi-geometric stack. Structure sheaf is a compact object in Q bar X. We'll now see truncations, also, and why we need them, why you need to understand truncations of quasi-geometric stacks. So you start off with a positive integer n and a quasi-geometric stack x, then the following are equivalent. So for every flat morphism from spec R to X, the infinity ring R is truncated, and there exists a faithfully flat morphism spec R to X where the infinity ring R is truncated. So our definition will be like, so for any positive integer n, a quasi-geometric stack X will be said to be truncated if it satisfies one of the above conditions. An example is like the classifying stack of a flat quasi-affine group scheme G over some commutative ring, say R. It's an example of a zero-truncated quasi-geometric stack. Okay. So now you start off with morphism. Oops, all right. So now we'll see what it means for a morphism to exhibit X. So we start off, so exhibit something as an n truncation of the target. So we start off with a morphism from X to X dash F of quasi-geometric stacks and a positive integer n. Then we say that F exhibits X as an n truncation of X dash if X is n truncated. And for every n truncated quasi-geometric stack Y, the composition with F induces this homotopy equivalence, the maps from Y to X and Y to X dash. Okay, and now we have the following result. So if you start off with a morphism of quasi-geometric stacks from X to X dash, with the morphism being affine and the unit map from OX dash to F lower star OX, exhibiting this F lower star OX as an n truncation of X dash and Q call X dash, then this map F exhibits X as an n truncation. X dash is just a characterization. Right. We'll now see that. Okay, there's another type here. An n truncated quasi-geometric stack is determined by its values on n truncated connective infinity. So suppose you start off with quasi-geometric stack X, which is n truncated for some positive integer n, and suppose, oopsie, seems, okay, so this is like a typo again. Suppose this X dash is the left Kahn extension of X that is restricted to this tau less than equal to n of C out n. Then the canonical map X dash to X exhibits X as a sheafification of X with respect to the QC topology, of course. All right, so how are we doing with time? So 36 minutes, that's not bad. So we'll now see the Tannaka statement for quasi-geometric stacks. So suppose we start with functors X and X dash from C out C into S hat and assume that X is a quasi-geometric stack and X dash is represented by a quasi-compact, quasi-separated spectral algebraic space. And suppose, so this is like this is like the category of functor category of symmetric monoidal functors, Q car to Q car X dash. Then we have a fully faithful embedding between the maps from X dash to X, and so there's like, so this is the way it's being functorially being recovered given this info, right? Defined, so that basically takes morphs from X dash to X to F upper star Q X to Q car X to Q car X dash. The essential image is basically spanned by symmetric monoidal functors F from Q car X to Q car X dash that satisfy the following. So firstly, F admits a right adjoint G. Then this right adjoint preserves small colimits, and the F takes connective objects of Q car X to connective objects Q car X dash. And for every quasi-coherent sheaf on X and like F on X and J on X dash, this canonical map, so this F tensor G of J and G applied, so G is the right adjoint, remember? G applied to F tensor J. So this is equivalence and quasi-coherent in Q car of X. So here's a consequence. So by the way, so this is something important, something that I want you to pay attention to here. I mean, something that comes up later. So the fact is that here it's also like, so here there's things going on with F and there's things going on with right adjoint G when we're talking about this. So that is something that you should keep in mind, and we'll basically try to eliminate anything like we'll try to have a statement where you can eliminate this dependence of G. So consequences, like if you start off with a quasi-geometric stack, then it is a hypercomplete sheaf with respect to the PQC topology. So we see that if this X dash is quasi-compact plus a separated algebraic, then the datum of this map X dash to X is equivalent to the datum of the symmetric monodal right D exact functor from Q co X to Q co X dash, which admits right adjoint G that preserves colimits and satisfies a projection formula. That was basically the last state. So what is the upshot? The upshot is that a quasi-geometric stack X can be recovered functorially from Q co X. So that is the Tannaka paradigm, the way I like to say it. This is Tannaka paradigm. So now we want situations to describe. So as I said, so the description is solely dependent on properties of function f rather than g. So this is where we'll see geometric stacks come into the picture. So moving on to the geometric stack world. Okay, so again you start off with a functor from CLC to S. It is said to be a geometric stack if it satisfies the descent with respect to the PQC topology. The diagonal is quasi-affine, and there exists a connective infinity ring spectrum R and a faithfully flat morphisms from spec R to X. So it is like a quasi-geometric stack with an affineness assumption on the diagonal. So we'll see like a few examples. So since cytochromatics, homotopy theory, I'll definitely give. I mean, and also because like this is the only example, a good example that I have a decent understanding of. So like this category of formal group laws for a commutative ring over R, it is a geometric stack. And the objects are basically these connective one-dimensional formal group laws. And you say that there's a morphism between these two these formal group laws F and F dash if you have an invertible power series G of X such that this formula is satisfied. Pretty standard. What the interesting one for me is like the derived analog. I'm pretty sure Lurie talks about both of these in his paper because that's where I got it from. Right. So you consider like complex periodic complex Bordism. Now here's one thing that you have to remember. So we were kind of there's one thing. So before talking about this example, let's go back for a moment and see in the definition we have this connective assumption. So this is something that's gonna be important to see in this like example. So first, like I start off by saying that you start off with a complex periodic complex Bordism MP, and since this MPN is even periodic, you're not getting connected. So what you do is you pass on to the connective covers. That's the trick. And then you basically get a simplicial object like by passing on to the connective cover, and you take the geometric realization. That will give you like a derived version of the of the geometric stack of FGLs. And so we'll now see like the Tannaka statement for the case of geometric stacks. So you start off the two geometric stacks X and X dash. Okay, you start off with functors, and the only assumption, okay, my bad. The only assumption is that X is a geometric stack. And then we have a fully faithful embedding again. Similarly, I've defined this category. This is like the symmetric monodal functors. Defined by, again, similarly, like F goes to F from X dash, F goes to F upper star. This again, this was essential images spanned by these symmetric monodal functions that satisfy the fact that they preserve small colimits and they map non-connective objects to non-connective objects and not flat objects to flat objects. So folks, so this is where I'll explain what I mean by tameness. But this is where these are the tameness assumptions that we want to get rid of. So Lurie also proves the following version with restricted tameness, like some sort of restricted tameness, as in like only like the flat has to go to flat, or we'll see. For a spectral geometric stack, so when I say spectral, it is like means geometric stacks which are modeled FPQC locally on spectra of connective infinity rings. So we start with spectral geometric stacks X and Y, with X being quasi-compact and having an affine diagonal. Then this map that we have, defined by again by F goes to F upper star, is an equivalence with essential limit spanned by colimit preserving symmetric monoidal functors F, such that it sends flat sheaves to flat sheaves. So this gets rid of one of the tameness assumptions. So Stefanich, what does Stefanich do? Stefanich proves that spectral version holds only when the diagonal is, okay, I think there's a typo. I mean to say that it also holds if the diagonal is assumed to be quasi-affine. Okay, so let's see. So this is something Stefanich proves in the paper. So you start off with spectral geometric stacks with X and X dash, with X being quasi-compact and having a quasi-affine diagonal. Then this functor, again, the one that I've defined. So this functor sending F to F upper star is an equivalence with essential limit spanned by colimit preserving symmetric monoidal functors F. And moreover, if X and X dash are classical with X having an affine diagonal, then the above are also equivalent. Okay, there's another typo, equivalent to this guy. So symmetric monoidal functor from Q call X hard to Q call X dash hard. In the classical setting, we think of so now, okay, so now the part of where I basically talk about like some just recall stuff that is over, and now we'll basically see what Stefanich is trying to do here. So in the classical setting, so now I need all of your attention. If you did not have your attention for it, it doesn't matter. But now I'll need your attention to everyone like live or watching the video. So in the classical setting, we think of the symmetric monoidal category like that. Okay, I don't know how to call it. So 2Q called APX or whatever. So this is like two category of sheaves of codindy abelian categories on a geometric stack X as a categorification of Q called hard. So this is the classical setting. So now moving to the categorical version, you have a functor like the spoke sections functor from 2Q called APX to graph 1. So this graph 1, I think, I've looked my notation. I think the notation that he uses is I think abelian. But okay, never mind. So yeah, I think abelian. So you start. So yeah. So you have a function like this, and you start off with C in this category, two category of codindy abelian categorical sheaves. And then this gamma of xc has a canonical action of this Q called hard, so that will give you a function that Stefanich, or I think Lurie calls it gamma ENH, that basically takes this so from this category to Q called X hard modules. So the categorification of Q called X hard being equivalent to the category of modules over the ring of functions on X is so that means that is equivalent to this being an equivalence basically. So that's the idea. So in the case of X being quasi-compact, a quasi-compact scheme, so this holds if and only if X is affine. Analogously, so Stefanich defines the geometric stacks to be, so it's missing a 2 here, so this is the same 2 category that I defined to Q called AB affine, if this function is an equivalence. So Lurie in SAG defines this function where he proves that it is fully faithful and X is quasi-affine and has an affine diagonal. So, but there are still tameness hypotheses. So Stefanich basically proves that you can get rid of them. So I think this is the last thing that I have. I think we're doing pretty good on time. So I was planning to wrap it up to 15 minutes, but here's what Stefanich proves basically, that if you have a quasi-compact geometric stack X with affine diagonal, then this function is an equivalence, right? Now, okay, there's for the first part of the second last. So let's see what the second last term is again. So this is the last. Okay, maybe I should have written this down. Okay, so this one. So okay, flat sheaves part. So for that, okay. Yeah, that is just really bad work with slides. Sorry about that. So yeah, there's the need to replace these Grothendieck abelian categories by complete Grothendieck free-stable infinity categories. We've seen what Grothendieck free-stable infinity categories are. You'll see more in the second and third talk. But why? You might ask why? Because it's just a convenient framework. Like, in general, to work with presentable stable infinity categories, which are like complete T structures. Now, analogous to the case of X being Grothendieck abelian for like X being a geometric stack for like any spectral stack X, this infinity category X and is complete Grothendieck stable for a spectral geometric stack X. So now, so what Stefanich does is to any spectral geometric stack X associates this category to PST comp X, quite a mouthful, but which is basically the category of quasi-coherent sheaves of complete Grothendieck free-stable infinity categories. As I said, like there's a need to replace this because we are working in the presentable stable setting. So we have a corresponding functor. So there's another like so there was a superscript. Now there's a subscript, I guess, comp. So this goes from this category that we defined to QCOM modules of this graph comp. So everything, all of this will be defined like in upcoming talks. So in SAG, Lurie basically proves that this is fully faithful when X is affine, quasi-compact with an affine diagonal. Stefanich, on the other hand, proves that you can like and yeah, there's tameness hypothesis Stefanich next result that basically proves that you can also remove this. So this generalizes it further to the case of quasi-affine diagonals. So this removes all the tameness hypotheses. So you start off with a quasi-compact spectral geometric stack X with a quasi-affine diagonal. Then this gamma in H comp is an equivalence. So that is the idea, and that is all I have to say. So that was your introduction to what's going to happen in the seminar and what we are expecting to see. So thanks everyone for listening, and I'll just stop here. Okay. So I'm assuming there's not going to be any questions for like the first talk, whereas it's basically what it's in DAG8 and SAG. But are there any questions about what Stefanich does? Like this, like just like a description of what, like a short version, like of what we're going to do in this whole seminar, like the proof sketch. Like, are there any questions? You see that there's a comment. Okay. So I'll wait for like a couple more minutes in case there are no questions, and then we can go to a post-recording discussion session. So are there any questions? Okay, I'll stop the screen sharing and I'll start the recording now.